Delaware Tech, Chemistry 100, Chemistry 110, Unit 4 Continued, Bond Polarity. In this unit, we're going to talk about the polarity of bonds, and to do that, we have to first talk about a concept called electronegativity. Electronegativity is a measure of how strongly an atom will attract the electrons that are involved in a bond between that atom and another atom. So if you have a pair of electrons making up a bond and two atoms that are being bridged by this bond, one atom may pull on those electrons more than the other. The atom that pulls on it more is called the more electronegative because it's pulling on those negative electrons towards it a little bit more. What is important, however, is not the individual electronegativity of any atoms, and these are shown here in the periodic table below. You'll see the numbers vary between 0.7 at the lowest all the way up to about 4.0 at the highest. The lowest are down in the bottom left-hand corner, and the highest are up at fluorine. They would include the noble gases, but most noble gases have not been involved in that many compounds, so the electronegativity is really not known well for those. So we're going to not consider noble gases and just consider the far right side of the periodic table being the halogens, chlorine, fluorine, bromine, iodine, etc. So you will notice that the highest ones are near fluorine, so fluorine, chlorine, oxygen. These are some of the highest electronegativity atoms, whereas the bottom left-hand corner, cesium, francium, radium, these tend to be the lowest electronegativity or the most electropositive atoms in the periodic table. And what is important is not the individual values, but the difference in the values between them. So if you have a bond, you always look at the difference. You take the higher number minus the lower number, and if that difference is 0, well, that will only happen if the two atoms are exactly the same kind of atom. Two fluorines, two hydrogens, two nitrogens, as long as they're the same, the difference will be 0. And in that case, those are considered pure, non-polar covalent bonds. Non-polar because one side is not getting the electrons or the negative charge near it more than the other side. If the difference starts increasing, so you have atoms where one atom is slightly higher than the other in electronegativity, there might be a small difference, a difference of less than 0.5. This is still considered very non-polar. It's not that significant a difference, and the bond is very covalent. When I say covalent, I mean the electrons are evenly shared between the two atoms. However, when you have atoms that are quite different in electronegativity, say oxygen, which is 3.44, and hydrogen, which is 2.20, well, then your difference would be 1.24, and that's a significant difference. That's above 0.5, but less than 2. Now you have polarized the bond significantly, and this would be called a polar covalent bond, and we'll show an example of that in the next slide. If you continue having atoms that are even more different in electronegativity, for example, if you took sodium, which is only about 0.9, and fluorine, which is close to 4.0, the difference now is greater than 2, and now the bond has polarized so much that all of the electrons essentially are almost always near the fluorine, and none of them are near the sodium, and therefore the bond has been broken completely or nearly completely, the covalent bond has, and now you have full-blown charges so that the fluorine is completely negatively charged, the sodium is completely positively charged for all intents and purposes, and therefore this would no longer be a covalent bond at all. It's not shared. It would instead be an ionic attraction between two opposite charges or an ionic bond. So when the bond difference, when the electronegativity difference is less than 2, it's still covalent, and they may have what we call partial charges. So here's an example with hydrogen bound to chlorine. Chlorine is very electronegative. Hydrogen is right in the middle, 2.2. And so if we show these values, you can see that the hydrogen is a little more electropositive and the chlorine is a little more electronegative. that means that the electrons are pulled towards the chlorine more often than they are towards the hydrogen in this shared pair of electrons making up the bond. So the chlorine attracts them more than the hydrogen, and we would represent that by this little dagger-shaped arrow. It's an arrow with a little line through it, pointing towards the direction where the electrons will be most of the time. And we usually make the line longer for bigger differences and shorter for smaller differences. And that just means that the electrons are near the chlorine more often, and that is because we have an electronegativity difference of 3.16 minus 2.20, or 0.96. If you remember from the previous slide, 0.96 is between 0.5 and 2, making this a polar covalent bond. It's still a covalent bond, but the hydrogen has a tiny positive charge, the chlorine has a tiny negative charge, and we represent that with the Greek letter delta, the lowercase Greek letter delta shown here. So this symbol right here, the delta plus means a partial positive charge, whereas the delta minus means a partial negative charge. And so bonds can be represented this way, and depending on the difference, we can tell which of those four types of bonds from the previous slide it is. In this case, this is a polar covalent bond.